That should be good. Well, good afternoon, everybody. Thank you so much for staying late in the afternoon. It's not an easy position. Thank you, Dan, in the schedule. But it's very exciting for us to be here because the topic is not only intellectually exciting, but it's really nice to see and interact with a like-minded group of people that are really worried about the future and are trying to think proactively on how to deal with what many of us believe is not exactly around the corner, but is coming nonetheless. So we're going to have two parts to this talk. I'm up for the very first part, which is to talk a little bit about climate change and what it's doing to the near coastal environment of California, because we need to understand that somewhat if we're going to project what's going to happen to human systems, what's going to happen to infrastructure, what's going to happen particularly to transportation. You have to really have some ideas about what's going to happen here. And so in full disclosure, I'll tell you I am not an oceanographer, so I'm going to do my best to summarize this accurately. And then I'll pass it over to John to talk about the work that we've done to build up topography, surface models, and get into GIS and work on transportation effects. Well, the very first thing that I want to mention that's been brought up today is, I think Sasha was the first to bring it up, is that we're working with models, and you have to have the models. And there's a series of them that we worked on in this project, and we worked particularly with 3 climate models. One here from the U.S., NCAR, which is the National Center for Atmospheric Research in Boulder, and also the Max Planck Institute model, and finally the French National Center for Meteorological Research. And that's in the center part. And then obviously on the left are all these emission classes, and we have 4 of them that we're considering. So we have 3 models and 4 emission classes: low emissions, medium emissions, and then higher end emissions. And so that'll show up in some of our charts throughout the day. Now what I want to go into is some of the broad scale influences on California. And the first thing I want to talk about that you've been hearing on and off all day is about the effect of El Nino and the Pacific decadal oscillation. And so I'm going to start with the second bullet point and the third, and then I'll do the first a little bit out of order. Obviously we have these El Ninos. All of you know about that. You probably have experienced them. And 82 and 83 and 97, 98 are kind of called the great El Ninos, and we've had a series, I guess, of minor El Ninos. And what can happen is you can get an elevation along the coast of 15 to 20 centimeters, or if you can't translate it that fast, it's 6 to 8 inches. And in sea level elevation, and this can go on for 6 months. And obviously, these El Nino events last for a while. They can last up to 18 months or so, but that's kind of the level of that's the scale at which they operate. And we also have the Pacifical decadal oscillation, which lasts much longer, decades, here, 20 to 30 years. And this graph is just showing you that these anomalies are the specific decadal oscillation and the La Nina or El Nino are evidenced by the sea surface temperatures, and that's how they can be detected. And there's anomalies in that there's areas that are either higher or lower than is to be expected. And the thing about the Pacific decadal oscillation, which is important, is that it has 2 phases. It has a cold phase and a warm phase. And right now we're in a cold phase, and this helps suppress the sea level, the relative sea levels along the California coast. And this is just, I mean, a very important thing going on. And believe it or not, our sea levels have been held down, and when this oscillation shifts into its warm phase, the rate of sea level rise will exceed the averages that, like say, the global averages, and we can have a fairly rapid rise in sea levels. The other thing up here, the first point is and I'll show you a graph of this later, is that when you just look at, when you're not looking at sea level rise, but when you're just projecting out the incidence and magnitudes of winter storms, the extreme storms, and this morning Sasha talked about a distribution, and the extremes are those that are remarkably higher or lower than all the rest, and we usually use percentiles like the top 1% of these storms or the bottom 1%. And so these top 1% storms, they're not expected to increase in incidence or magnitude. And I'll be talking about that more and have a graph. The other thing I wanted to bring up is the relative sea level trends. And there's some nice little applets on the internet you can go to, and you can specify years. You can see where you can get this. And this is over a 60-year span, and showing you the relative sea level rise along the Pacific and here in the Gulf. And the thing is, you've probably heard today that the altimetry, which is basically satellite-based measurements, show about an average of about 3 millimeters a year. And but here, for example, up in this area, it's actually in a decreasing trend, and in the California coast is on an increasing trend, but we're at 1 or 2 millimeters instead of 3, so it's relatively suppressed, and that's what we mean by the PDO, or Pacific Decadal Oscillation, suppressing the relative sea levels. We could have had larger gains if it had not been for that. Now, just a minor point, but relative sea level is measured, this graph over here is telling you, you could measure from the center of the Earth sea level, but the relative sea level is measured to a point in the sediment layer, and that's kind of something you probably don't have to dig into too much, but that's where it's measured to. Now I want to talk about these other things which are quite important, which are the sea level rise, the winter extreme wave heights, and the wave run-up and flooding, because what we're concerned about is the effect on infrastructure, and so we need to know what's the combination of these things, what potentially could they be. Well, throughout the day you've seen some evidence. Here's a graph from 1800 to 2000, tracking like San Francisco, and you can see a trend of gently increasing, and Sydney was relatively flat, but Honolulu was increasing. And this is how you can have in different parts of the world kind of a decreasing trend, an increasing trend, or almost, what? 3 for me? Okay. Okay, 3, that's no problem. Okay, 3 minutes for me. All right, okay. Great, 3 minutes is the 3 minutes it is. Anyway, the mean sea level rise that's projected, if you use 3 millimeters, projects out like that to the end of the century, but the models project much higher sea level rises between 1.4 and 1.6 meters or more, and that's what the models are showing. And let me also talk about these winter extreme water levels. Looking at, again, these 99th percentile ones. Historically, San Francisco, which is in green here, has been around 26 centimeters, which is about 10 inches. These are the winter storms, and the projections are bracketed around between 20 and 30 on average, and you can see, though, there's a lot of variation and oscillation around those means. So we're talking about the trends. So the winter extremes are projected to be fairly similar to historical. Now, you also have a thing called wave run-up. You know that waves don't just sit there, they actually run up the beach, and in the winter they have more energy and they go further up the beach. And so wave run-up's important also when you're considering flooding. And one thing is that without considering sea level rise, these models predict that the counts of these extreme run-ups are going to be fewer, but we'll see later that when you add mean sea level rise, this situation changes dramatically. And this is a wave run-up height that basically on average these models are showing there'd be about 2 meters of wave run-up height. This is a very important graph because this one shows if you take the mean sea level rise and run-up and you put them together in a graph like this, you can see that now it's going up into 3.5, 4 meters or whatever. That's the combination. And what happens with that is the counts of these extreme run-up events with sea level rise, they switch from being relatively low, 100 or so, to end of the century being 6, 7, 800, a factor of 4 or 5 greater. This can lead to very severe conditions for flooding. And this is just to show you the components. You have what's called a still water level, and you have wave height during storms. And then you can add on top of that sea level rise. And so, you can see that, you're moving up the shoreline and the effect is much stronger. Lastly, and I want to show you a thing called a return interval. And these graphs going up from blue to red are like increasing sea levels. And so this bottom one, the way to read it is to say something that might take 100 years to occur at a certain level right now, let's say without sea level rise. When we add sea level rise, something that used to take 100 years may take only 1 year. and so now, you've seen this in the news where flooding, they'll say this is a 100-year flood event, and then 2 years later there's another 100-year flood event. Well, the dynamics of the system are changing, and that's what we're saying here. When the dynamics change, what used to be a 100-year flood event could be much longer. And with that, I am ready to turn it over to my colleague, John Racky. Thank you.
Gee, I thought you were supposed to wait until the end, so I wouldn't feel bad if no one claps for me. All right, so we built a better model, and we had more up-to-date data. We have to thank a lot of people because it took a lot of people to build this model and get it to us in time to do this research. It was completed, I think, in August. We received the data, and it was a LiDAR, pulse-based type collection of data for the surface, and that would be the digital elevation model, and this is the upper level, or when it hits structures and infrastructure and trees, and that's actually a zoomed in version of it, and those are actually trees and leaves on trees that get hit by the model. So it allowed us to build a much better model, and this was the coverage over the Bay Area, and we chose the Bay Area because we were familiar with it, but also because I think it represents a critical piece of infrastructure that will be hugely impacted by this climate change and sea level rise. And of course, if we look at what Greg just told us, that this is going to increase and we're going to get these events happening more frequently. And then this is what it looks like. So here we are, the blue area is no sea level rise, and the red area is with 150 centimeter sea level rise. And this, of course, is the inundation from these extreme storm events. And that looks sort of impressive, but it's zoomed way out. So we'll go and we'll look at some of this up close. And of course, this is what happens, and this actually is a picture just east of our site. A graduate student happened to be out on another research site of ours the day of a storm, and that is the infrastructure and the road network right near the edge of the bay getting devastated. And we see this all the time because we go out and we repair these things, and we see someone repairing and say, oh, they're repairing a crack in the road. And then the next storm and they're repairing again and again. Well, how does this add up? Well, here's our digital elevation model and our digital surface model, which we built. And we can actually then take these models of inundation, of sea level rise and inundation based on these extreme floods, and we can flood the area. So we started flooding the area, and this is a combination of older and newer work looking at some of the areas in the Bay Area that do get flooded as sea level rises and we have these storm events. And of course, it's not just theoretical, because here we are just in January of this year, and we have this airport in Australia gets inundated and flooded. So we're not alone in this, and we thought that was a good slide to precede this one. Now, earlier you may have heard that the San Francisco airport gets inundated at a certain sea level rise, and it was the older research. The newer research shows us that at 2.4 meter peak water level, it's still okay. That's because there's a levee around that airport. But at 2.5, it's not okay, and it gets flooded, and we lose the runways. Well, obviously, what we can do is we can just build higher levees. We keep doing that, and that'll keep people in jobs and create jobs. But maybe there's another way of looking at this. So we felt that, we pick on the transportation network. So not just artifacts, not just these institutional things, the infrastructure that happens to be sitting there is going to get flooded, but we thought we'd take on something a little bit more complex and dear to our hearts, because we all can identify with the transportation system. We have to navigate through it all the time, and it really does affect movement. And we decided transportation as an infrastructure because the interesting thing is no one controls it. No one entity controls the entire transportation network. There's many different organizations, and they don't coordinate very well, and they're always pointing the finger at each other. So it's always good to take something on that when it gets devastated and things are broken, everybody's pointing the finger. It's your fault. So here we are, and this is just a zoom in on Richmond, California. And what we did here, we thought we wanted to show the devastation and movement. We wanted to show how movement impacts based on this sea level rise, these storm inundation, and as you start to lose infrastructure, it just doesn't damage the road, it actually damages the connection. And we thought we'd like to do it locally, and what do we have locally? Well, rather than picking up a bunch of fictitious points and trying to look at how the infrastructure breaks, we thought we'd go to first responders, because in the event of a storm, you really hope that that first responder can get to you to save you. And of course, this is what happens when there's no sea level rise. And this turns out the first responders they're ubiquitous in space, really. They're well located. They do this on purpose so that they can get to all the citizens and save them in the event of a disaster. Although I did notice that one thing, it's quite orange, and so it takes 6 or 7 minutes, and it's up in the hill area. So we assume that they have a hard time going uphill. We started then increasing sea level rise and causing inundation and rerunning our models. So essentially we ran first responders from their station out to every location in the network. And this network's a constrained network, and it's weighted based on what the road capacity or capability is. And we made the assumption that first responders have lights and horns, and they can usually go at a fairly constant rate. At least the rate that the road specifies. And you see it doesn't take long before some areas become really isolated, even one that happens to be not that far away from a first responder. It just so happens, though, that the road that the first responder would use to get there has actually been inundated and it's gone. We then thought, okay, when we went around the entire Bay Area, and we're just showing you Richmond, looking at that, looking at the localized effect. And then we thought, well, we'd want to look at the regional effect and impact as well, because what if I lived in Contra Costa County? I'm not anywhere near the ocean. That's why I bought there. My house is at 600 feet above sea level, and my summer home is at 600 feet above sea level. It's somewhere about 600 feet. I like to be there, and I figure I'm not going to get impacted by this. But it turns out I am. And so we thought, what really is the key piece of infrastructure, the skeletal part of the regional network, and it's the highway system or the interstate system. And so we took those interstate systems that are just around the Bay Area. In our model, we ran everything. We ran all the roads and all the freeways that are inland as well in our model, but we just wanted to show these key points because we thought they were key nodes in the system. So how would that impact me regionally? And of course, we ran the model, and this is what we got. We ended up, these are node to node or point to point between those key intersections that really affect most of the commute. And it turns out that the Bay Area gets devastated when we have, the 100-year prediction, 100 years out from now, where we have a 4.1 peak water level. So that's sea level rise and one of these extreme storm events, and it takes out the infrastructure. And we see here it increases, over 100 times. And at this point, as my great-grandfather used to have a canoe and a paddle, at this point I'm going to tell my great-grandchildren, make sure you have a canoe and a paddle, because that's the only way you're going to get across. If you look at this, it really takes you 11 hours to get, by land, to get from Oakland to San Francisco. So a canoe makes sense. Or we can use this to rethink the planning of our infrastructure over the next 100 years, because it's not going to cost us more. Everybody thinks, how much is that going to cost? It's not going to cost us more. It's just a change in thinking, and we'll change our eye or change our focus on the ball. And if we do that, we can redesign an infrastructure that won't be so critically impacted. And then we decided we wanted to look at the hinterland around those key nodes. So those were key nodes. They do get impacted, but what if you can't get to the key node? And so we looked at that, and we modeled it and looked at with, again, this 4.1 peak water level. And we find not only many of the key nodes are completely gone in the sense that they're not accessible anymore, but it becomes difficult for people to access some of the nodes. So it's pretty clear we have to take a look at this. If we're not going to be able to stop the sea level rise, then we need to focus, and our mitigation should look at maybe redesigning a new transportation infrastructure. And again, no one entity's in charge. It's state, federal, county, city, local, etc. Well, our conclusions were that 1.4 meter sea level rise in combination with a 100-year storm event will have pronounced effects on the transportation network in the Bay Area. And of course, Greg told you, wait a minute, every 100 year might happen every year. So we're going to get this constant bombarding of our transportation infrastructure. And in the Bay Area, we've faced a few accidents where we had some of this infrastructure crumble and stay out of commission for 30 days, I think. And it was devastating on everyone's commute. And then using an origin-destination model, we found that the east-west movement is impacted 3 to 11 times. The north-south was less, and that's because there's more redundancy going north-south. There are more highways. There's inland highways that can actually connect us. So we should start thinking about that. Maybe we ought to be thinking about putting things inland as well. We also show several critical nodes. They become inaccessible with the peak water level as well. Well, we thought about what are the next steps for the research and data needs, because this was sort of the first time the group attempted to look at impacts and really look at the impact not on the direct thing that was impacted, but on those regional movement impacts. And so we went down a list, and really we need to come up with more advanced hydraulic modeling. We realized this. We built an incredible surface model and infrastructure model, and then we realized, and we have these great models affecting sea level rise, but now we realized, well, wait a minute, inside the bay it does oscillate a little differently than outside, and we know we need to go there. And in addition, we need to advance these water flow research models, and we've been doing this in another research project, just starting to do this, because when levees break, water in behind the levees will travel differently, and we need to dynamically do this to understand what infrastructure should be armored, because we may end up come up with a completely different armoring strategy for armoring some of our key pieces of infrastructure, and then let some of it go. Just let it go, because it's not worth it. Over time, it will just continue to fail. And then we need really a comprehensive inventory of the levees. We have many, many levees, and we really don't. We now know we've measured the tops of them, but if I could show you a slide of how levees could fail, they fail in about 12 different ways, and we really don't know this. How are they going to fail? And we need to assess the vulnerability of the wind and waves, and also move out into the Sacramento-San Joaquin Delta. So this is where we kind of see this research, or this kind of research going after the modeling we've done. And then a few more next steps, because we were asked to come up with, well, where do you think this ought to go? And we had our group of 9, I think, and we said, collectively send us your wish list. And so this is a combination of everyone's wish list. Thank you.
John, Greg, thank you very much. Fascinating.